We are really approaching the end of this curriculum. We only have two sections left to cover. And today we are going to be covering our section 11.3, which is our ellipses or ellipses. I don't know how you guys pronounce it. I guess I'll call it ellipses. What are our objectives for this section? Being able to graph an ellipse with center at the origin, find the equation of an ellipse with center at the origin, and then being able to graph an ellipse where our center is no longer at the origin and we have some vertical shifts and horizontal shifts taking place. So first, let's define what an ellipse is. An ellipse is all points in a plane where the sum of the distances from two fixed points is constant. And so each of the fixed points is known as another vocabulary word, which maybe I'll use a different color for this, a focus of the ellipse. So let's really look at this from a more graphical standpoint. We have an example of an ellipse here. And then we have our foci, which are labeled F1 and F2. And so the line containing the foci is called our major axis. So we have our major axis here, and I'll highlight our major axis over here accordingly. And then I can even color code our F1 and F2. Our F1 is right over here in light pink. And then our F2 is over here in orange. And the midpoint of the line segment joining these foci is the center of the ellipse. So why don't I highlight that center point in blue, which is the midpoint of the line segment joining those two focal points. Let's continue. We have the line through the center and perpendicular to the major axis is our other axis, known as our minor axis. So why don't we put that in red so you can really see all of these visuals taking place. And then we have the 2 points of intersection of the ellipse and the major axis are known as our vertices. So think about parabolas or absolute value functions. That vertex point is where the direction is changing from either increasing to decreasing or vice versa. Well, the same very similar concept is applied to ellipses. It's just we're really honing in on the vertices being and stemming from the major axis and not the minor axis. So these are not vertices. It's always going to stem from our major axis. So why don't we label and color code our vertices V1 and V2 in yellow. The distance from one vertex to the other is the length of the major axis. So V1 and V2 gives you that entire length of your major axis. And then the last thing to mention is just the symmetry, which is another cool characteristic of ellipses. Uh, the ellipse is symmetric with respect to its major axis, and it's symmetric with respect to its minor axis, and it's symmetric with respect to its center. A lot of cool characteristics here. And then this is just a visual of looking at your minor axis being smaller in length compared to your major axis, or it being I shouldn't say. I mean, major axis is always going to be larger in length, but the differences between these two is looking at it from an XY coordinate plane. So if you were to draw your XY axis in this first example, your distance from x1 to x2 is much greater than your distance from y1 to y2 on your y-axis. But then in your second example, your distance from your x1 to x2 is much smaller. And this will, when we look at our general form of an equation of an ellipse, where those denominators are a squared and are b squared, that's where these differences between your horizontal distance and your vertical distance play in. And so your A value will change depending on if it's going to be smaller in length versus your B value. And we can talk about it more on this slide where you really see our standard form of our equation of a circle. I keep saying circle, but I'm talking about an ellipse here, right? Circles have the same length all around. With an ellipse, it's not the case. So our standard form is x squared divided by a squared plus y squared divided by b squared is equal to 1. And so our a is always representing that distance horizontally. If it's stemming from the origin, it's representing that distance on your x-axis, whereas your b is representing your distance vertically. And again, if we have that center point stemming from the origin, we're just solely looking at that y-axis. So technically, if our a value ends up being larger, then we're going to have an ellipse that has that longer horizontal distance. Whereas if your A value is much smaller than your B value, then we are going to have that horizontal distance be much shorter. And so your ellipse is going to look more like a stretched out long face instead of a watermelon. And then this slide is just putting all of our characteristics together, really emphasizing, okay, what does our A value tell us, especially stemming from that origin? It tells us our distance from our center point to that edge point of our ellipse. And then our B value tells us the same thing, just in that vertical direction. And so we can very easily identify what our x and y intercepts are, and then what we have stated up here in terms of the inequality form is just stating where your major axis lies, aka is it going to be on your x-axis because now you have that longer horizontal watermelon looking guy, or is it going to be on your y-axis where you have that elongated oval looking face? And so there are 5 steps with graphing an ellipse, but I think it's better if we go through it step by looking at a concrete example. So this brings us to our example 1, where we are asked to graph this ellipse. X squared over 4 plus y squared over 9 is equal to 1. So let's write out our standard form. Which means now we can very easily identify what our a squared and what our b squared is. A squared is equal to 4, which tells us that a is equal to the square root of 4, which gives us plus or minus 2. And then our b squared is equal to 9, which tells us that our b is equal to plus or minus 3. And so now we can easily identify our x and our y-intercepts. And so our x-intercepts are at -2, 0 and 2, 0. So maybe I'll write this up here. X-intercepts, y-intercepts, -2, 0, and 2, 0, whereas my y-intercepts are -0, -3, and 0, 3. And now we can graph our center point. We're stemming from the origin. So 0, 0. Let me maybe bring a graph in for you. And so there you have it. I plotted my points on a graph that I brought in, and then we can go ahead and draw our ellipse. Try to make it look a little bit more accurate. There we go. And it's done. So let us do another example together, and then I'm gonna copy and paste this so that we have it for the next example as well. Okay, I'm gonna bring that one in. Great. And so now we're asked to graph x squared plus 4y squared equals 16. And you want to remember our standard form, x squared over a squared plus y squared over b squared equals 1. We want to get it into that format, meaning we should divide everything by 16. So now we're looking at x squared over 16 plus 4y squared over 16. Well, 4 over 16 is the same as 1/4. So we can replace this with just y squared over 4 is equal to 16 divided by 16, which is 1. And now we can very easily identify our a squared, which is 16, which tells us that our a is the square root of 16, which is plus or minus 4. And then our b squared is 4, which tells us that our b is the square root of 4, which is plus or minus 2. A is along our x-axis. We have our center point at the origin once again. And so we have our x-intercept at -4 and at +4. And then our y-intercept is at -2 and +2. And now we're going to go ahead. Let me just make sure that this is 4. 1, 2, 3, 4. Yep, we're good. 1, 2, 3, 4. Yeah. And now let's connect the dots. And there we have it. This is our ellipse. Okay. So let's continue on to our second objective, which is finding the equation of an ellipse with center at the origin. So it's now very similar to what we've been working with, but now instead of graphing the equations that are given to us, we're going to be given graphs that we need to find the standard equations for. Let's take a look at our example 3, where we can very easily identify our A values to be plus or minus 4, and our B values to be plus or minus 3. So when we are asked to find this equation where our origin is 0, 0, we're just going to look at our standard equation of an ellipse, which is x squared over a squared plus y squared over b squared is equal to 1. And now we just plug in our a and our b values. So x squared over 4 squared, which is just 16, plus y squared over 3 squared is 9. All right, let me fix this. My pens are glitching. Here, it's better. Is equal to 1. And that's it. We're done. We're now on to our third objective, which is being able to graph an ellipse when our center is now not at the origin. And so our standard form for an equation of an ellipse, where this is the case, is now this whole x minus h in parentheses squared and y minus k in parentheses squared in our numerators. And that h comma k represents our new center point, where again, it's now no longer at the origin. And if it is, then our h and our k is just 0, and then it just goes back to the whole x squared over a squared plus y squared over b squared equals to 1. Okay. So let's look at example 4, where it's really in that format. So there's not a lot of manipulation that needs to take place here. Our h is equal to 3, our k is equal to 1, so this very easily tells us that our center point is equal to 3 comma 1. And then our a value is plus or minus 3, aka the square root of 9. Our b value is plus or minus 2, aka the square root of 4. And now we have all of the information that we need in order to graph out this ellipse. So let me bring in my graph again. We're going to go ahead and first plot our center point at 3 comma 1. 2, 3 comma 1. And then our a, every 3 points to the left of our center point, 1, 2, 3, we are going to plot our endpoints. So that's our minus 3, and then 1, 2, 3. This is our plus 3. And then we're going to go up 2 from the center and down 2. And now we are going to simply just connect the dots. And there we have it, our ellipse. And so don't forget to write in the equation over here. I haven't been doing that just for time purposes. Right, example 5, which I believe is the last example, yep, for our section 11.3. And so we are asked to write this equation in standard form, and then we are also asked to sketch its graph. So I'm going to put in the graph there as like a place marker for space. And then I'm going to write out my equation, and I'm actually going to pair my x's together. So we have our x squared minus 4x, and I'm going to leave a little space, and then we have our plus 4y squared plus 24y, and then I'm going to bring that 24 over to the other side. So equals negative 24. Okay. Now, the thing that really stands out for me is that 4y squared. I want to make sure that the coefficients of x squared and y squared are 1. So I'm going to, oops, don't know how that happened, but I'm going to divide everything by 4. So divide this by 4, divide this by 4, this by 4 to get us that 1. Divide all of these by 4. Okay. So now we're looking at our x squared minus 4x. Again, I'm going to create a little bit of space. Plus our y squared plus 6y, a little bit more space, is equal to negative 6. Great. Now, very similar to circles, when we want to get out of this general equation format and put it into our standard form, we need to be able to complete the square, but because we have two different variables, our x and our y, we are going to be completing the square 2 separate times. And when you complete the square, you want to think of, okay, what is my special key? And so my special key in both cases is this b over 2 in parentheses squared. So I'm going to put that on that left-hand side for my x's and then on that right-hand side for my y's. And so my b value for my x, I'm going to just hone in on that numerator for a second, and then I'll show you how we manipulate it later on. So I'm going to use that negative 4 for my b for my x, and then I'm going to use 6 for my b for my y. Okay. So we get negative 4 divided by 2, which gives us negative 2, and then we square that and we get 4. That's the constant we'll add to both sides in a moment. With our y's, we get 6 divided by 2 in parentheses squared, which is 3 squared, which is 9. And that's going to be what we add to both sides for our y's. Now, when we add it to our x, notice how we still have that divided by 4. So technically, we're not adding 4 to both sides. We're just adding 1. So to that negative 6, and maybe I'll do some shrinking, I'm going to put in a plus 1. That's a little cleaner. And then for the y's, we added that plus 9. And whatever we do to one side, we have to do to the other. Okay. So now I'll create a line so that we can really simplify this a bit more. We're now ready to complete the square with both cases. We can complete the square, aka factor this now into x minus 2 in parentheses squared. This is all divided by this 4. And then for the y, that numerator can be factored into y plus 3 in parentheses squared. And then our denominator is just 1 if we wanted to like put this all over 1, right? And then we have this right-hand side, we got 9 plus 1, which is 10, and 10 minus 6 is 4. So we have this is equal to 4. So we're very close to being done. The very last step is, remember, standard form, we need that right-hand side to be 1. So we're actually going to divide everything by 4. And when you divide everything by 4, these two separate fractions, by keep, change, flip, what's going to happen here, I'm just going to copy and paste the numerators now because that's not changing. But the denominators will now change. And our new denominators are going to be 16, because 4 times 4 gives you that 16, and 4. And then we get 1 And now it's officially in standard form. Let me shrink this so you can see it a little bit more clearly. Much better. And we can clearly state, okay, our center point is 2 comma negative 3. And then our a value is the square root of 16, so a equals plus or minus 4. And then our b value equals plus or minus 2. So last but not least, we're also asked to sketch this out. So let's go ahead and do that on this graph over here. And so let's plot our center point, 2 comma negative 3. We're going to move our in the horizontal direction, 4 to the left, 1, 2, 3, 4, plot, 4 to the right, 1, 2, 3, 4, plot, and then 2 up and 2 down. 1, 2, 1, 2. So let's connect the dots. I'll fix that. Let's try it one more time. Yeah, that's perfect. And we're done. So that completes this section 11.3. And our last section is going to just cover solving systems of nonlinear equations. I hope that this was helpful, and I will see you guys for our last video for pre-calculus. Take care. Have a good one. Bye.